Hello everyone, myself Abhishek, and today we are here to discuss how heat conduction takes place within the nuclear heat source. So, first we will talk about what is heat conduction. So, heat conduction is one of the way of heat transfer from one place to another place. There are mainly three ways or three modes by which heat can be transferred from one position to another position. These are by conduction, by convection, and by radiation. The first two modes requires medium for heat transfer, while the third way do not require any medium for heat transfer. So heat conduction is the transfer of thermal energy within a body due to a temperature gradient without bulk movement. If there is a bulk movement, then that mode of heat transfer is known as convective heat transfer, not conductive. And conductive heat transfer mainly occurs in solids, especially metals. Molecules do not leave their main position for energy transfer. They just vibrate at the main position. So the mechanism of heat transfer by conduction is lattice vibration and free movement of conduction electrons. There are many common examples in day-to-day life, like hitting a metal rod or engine parts getting hot. And next, how this heat conduction is studied. So, for the study of heat conduction, there is a scientist who gave his law, which is known as Fourier's law of heat conduction. This law states that energy flux is proportional to the temperature gradient in the direction of heat flow. That is, Q is proportional to minus of dT by dx. And the equation we got is Q equals to minus K dt by dx. This dt term is negative and dx term is positive. So the ratio of a negative to positive number is always a negative. So to get the Q positive, we have multiplied that dt by dx term by minus 1. So we got Q equals to minus K dt by dx, where K is known as thermal conductivity and it has a unit of watt per meter per Kelvin, and it is a materialist property. Its physical significance is it shows how fast or how easily heat can travel from that material. Higher the value of K, more easier for heat to travel through that material. dT by dx is temperature gradient, which has a unit of Kelvin per meter. Next, we will see how what is a nuclear heat source. So, nuclear heat source generates by a type of reaction which is known as nuclear fission. So, nuclear fission begins when a thermal neutron, that is, a slow moving neutron having very low kinetic energy, when it collides with the nucleus absorbs the neutron, and upon absorbing the neutron, nucleus becomes highly unstable. This is because when neutron enters the nucleus, it carries some kinetic energy, and binding energy of neutron is also added to the overall system. And this overall addition or increment of energy drives the nucleus into a very excited state. So it splits up or breaks up into smaller fragments. If we take the example of a very common material, uranium 235, then upon neutron absorption, it breaks up into two smaller physical fragments. One is krypton 92, second one is barium 141, and it also gives some additional neutrons and some form of energy. Why we need to study this topic? So With the knowledge of this nuclear reactor, we can prevent reactor meltdowns, we can increase the overall efficiency of nuclear reactors by managing effective heat transfer, and nuclear reactors possesses many applications in power plants, spacecraft, and submarines. So uh, we see how heat generation takes place in nuclear material. So we have taken the example of uranium-235, which on neutron absorptions splits up into barium and krypton, and these two smaller fissile fragments. They move with a very high speed and they possess very high kinetic energy. Whenever one nuclear fission takes place, it nearly emits 200 mega electron volts of energy, and out of that 85 to 90% of total energy is contained by the kinetic energy term only. Since smaller fragments moves with a very high speed, when they collide with the surrounding atom, they lose their energy in the form of heat, and this results in overall heating of the fuel element. And some of the energy is released in form of gamma rays and beta particles, and these particles are absorbed by the surrounding material, and they also contribute to further heating of the fuel element. They consist of 10 to 15% of the total energy, and the fast moving neutrons, they can be absorbed by the other fissile nucleus so as to sustain the chain reaction, or they can be slowed down by using moderators like water, graphite, or heavy water, so that they can become thermal neutrons, that is, a very slow moving neutrons having low kinetic energy. Since chain reaction goes on, so there is a continuous heat generation within the fuel element, and this heat transfer takes place from inside of the fuel element to outside, and a temperature gradient always exists within the fuel element, and as heat transfer takes place uh, from inside to outside, surrounding each fuel pellet, there is a layer of material which is known as cladding. Cladding means outer layer or a layer that covers nuclear fuel pellets inside the fuel rod. And if we talk about importance of this cladding, so cladding have a very much importance as they prevent release of radioactive fusion products from the fuel pellets to the reactor coolant. They also increases heat transfer rate by increasing the area of contact. They also have seen holding fuel pellets together and maintaining the overall geometry of the fuel rod during the entire heat transfer operation. And the cladding material has a high thermal conductivity as compared to the fused material. As heat generation takes place inside the fuel, and fused material's thermal conductivity is very less. And if the thermal conductivity of cladding's material is also less, then there will be very tough for heat to travel. So it can result into overheating, which means localized hot spots, or it can lead to potential fuel damage, or it can lead to safety risk. So thermal conductivity of cladding's material is always greater than that of fused material. However, there is a small gap exists between fuel pellet and coolant, and that gap is filled with helium gas. This is done because as to increase the heat transfer rate by increasing the area of contact. And why helium gas is used? Because as compared to other noble gases, helium gas has a very high thermal conductivity, and its neutron absorption factor is also very low, which means It will not absorb neutrons, so it will not disrupt the functions of a nuclear reactor. And the coolant carries away the heat, keeping the fuel at a manageable temperature. And from outer surface of cladding, the heat transfer is governed by Newton's law of cooling, which is Q equals to H into delta T, temperature of cladding minus temperature of coolant. So once the coolant absorbs the heat, that coolant is boiled up, converted to steam, and then it is struck on turbines, then turbine rotates, and this is how electricity is generated.
Now I am going to discuss heat conduction with a nuclear heat source. Consider a spherical nuclear fuel element. It consists of a sphere of reasonable material with radius Rf, surrounded by a spherical shell of aluminum cladding with outer radius Rc, with constant outer surface temperature T0. Inside the fuel element, fission fragments are produced that have very high kinetic energies. Collisions between these fragments and the atoms of the fissionable material provide the major source of thermal energy in the reactor. Such a volume source of thermal energy resulting from nuclear fission we call SN. The unit of SN is calorie per centimeter cube into second. This source will not be uniform throughout the sphere of fissionable material. It will be the smallest at the center of the sphere. For the purpose of this problem, we assume that the source can be approximated by a simple parabolic function given by Sn is equals to Sn naught 1 plus b into r upon rf bracket whole square. Here, Sn naught is the volume rate of heat production at the center of the sphere and b is a dimensionless positive constant. Now we have to derive the expression for temperature profile for both elements. If Kf and Kc are thermal conductivity of reasonable material and aluminum cladding, assume two constants in given temperature range with given value of Rf, Rc, T0 and B. Here in this diagram, it is shown the aluminum cladding at the outer surface of the sphere and the fissionable material is inside the core of the sphere. Here is the temperature profile shown. Now, the solution of this question is first we will show the assumptions. First, steady state conduction. It is because temperature does not change with time. Radial symmetry. As we can see here, temperature varies only in the radial direction r, not with angle theta or length z. Uniform internal heat generation. Here we see constant volumetric heat generated Q, whose unit is watt per meter cube. Now fourth, constant thermal conductivity. Thermal conductivity K is independent of temperature. Fifth, no internal fluid flow. Here we can see pure conduction, no convection inside the solid. Sixth, boundary temperature. We can now the terms are Q, heat generated per unit volume, watt per meter cube. K, thermal conductivity, watt per meter Kelvin. The temperature which varies at R, which is a radius of sphere. Now coordinate system. The coordinate system is spherical, whose origin is at center. Temperature is constant with theta. Due to symmetry, we can see temperature does not vary with theta. The second, temperature is constant with phi because due to 1D flow. Temperature is only the function of R. You can see here the terms theta and phi are not related with temperature, only the term radius varies with temperature. Therefore, heat only in R direction. Now we will see shell energy balance. Rate of heat energy in by convective transport minus rate of energy out by convective transport plus rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of work done on system by molecular transport minus rate of work done by system by molecular transport plus rate of work done by system by external forces minus rate of energy production is equals to 0. Now we can see here the terms rate of energy in by convective transport minus rate of energy out by convective transport is 0 because there is no convection here. Rate of energy in by molecular transport, this term will be present. Rate of energy out by molecular transport, this term will also be present. Now, the rate of work done on system by molecular transport, it will be 0. And rate of work done by system by molecular transport, this term will also be 0. The since no external forces are there, so our rate of work done by external forces will also be 0. So only three terms will be there: rate of energy in by convective transport, rate of energy out by convective transport will be 0, and the work done terms will also be 0. Only the molecular transport functions will be present. So rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of energy production will be equals to 0. So rate of energy in by conduction at R minus rate of heat out by conduction at R plus delta R plus rate of thermal energy produced by nuclear fission is equals to 0. We can see here the rate of heat in by conduction at R is given by flux into area. The flux is denoted by Q and area is given by 4 pi R square here. The first term will be 4 pi R square into Q R of F at R. The second term rate of heat out due to conduction at R plus delta R will be minus of 4 pi R square Q R of F at R plus delta R. Now rate of thermal energy produced by nuclear fission will be given by SN into volume, where SN into volume can be written as 4 pi R square delta R. Now now by multiplying by minus 1 and dividing by 4 pi delta r, we will get the equation as r square pr of f r plus delta r minus r square pr of f at r upon delta r is equals to d upon dr of r square pr of f. Now we can see here the we can assume one limit delta r tends to 0 for easy calculation. Now given heat generation is Sn is equals to Sn naught 1 plus B into R upon capital R F of whole square. Now we will combine equation 1 and 2. The equation 1 is limit delta R tends to 0 R square into QR F R plus delta R minus R square QR of F at R minus upon delta R is equals to D upon dr of R square QR of F, which is equals to Sn into R square, and Sn is equals to Sn naught 1 plus B into R upon R e power whole square. Now by combining these both equation we will get D of dr of R square into QR of F is equals to Sn naught 1 plus B into R upon R F the whole square into R square. Now differential equation for cladding is given as d upon dr into r square qr of f is equals to Sn naught 1 plus b r upon rf whole square into r square. As we can see here, no heat is generated, so Sn will be 0. So therefore d by dr of into r square qr of c is 0. And also rearranging equation number 3, we can get d of dr of into r square of pr of f is equals to Sn naught r square plus b r की power 4 r whole square. We just substituted r square inside the bracket and we got this equation. Now we will integrate the equation. Since these two equations, since this equation is a function of r and the term inside is r square qr of f, now we will integrate both sides. After integrating, we will get r square pr of f is equals to Sn naught r square will become r cube by 3 plus b small r to power 4 will become r power 5 by 5 into R F whole square plus constant C value count. Now after rearranging equation, we will get QR of F is equals to Sn naught R by 3 plus B R F whole square R cube by 5 plus C1 F by R square. Basically, we divided the whole equation by R square. Now, by our equation, we see that no heat generation is present. So d by dr of R square QR of C is equals to 0. Now we will integrate this equation. After integrating this equation, we will get R square QR of C is equals to plus C1 whole C. Now rearranging the equation, we get QR of C is equals to C1 of C upon R square. It's just divided by R square. Now QR of F as stated before is equals to Sn naught R by 3 plus B upon R F whole square plus into R cube by 5 plus C1 F R square and QR of C is C1 by R square at C. We get flux at location C and location F. Now we will solve these equations by applying boundary conditions.